This is the third part of our discussion on derivatives of complex valued functions. So far, we have studied what is derivative of a complex valued function. Also, we discussed some simple examples where we calculated the derivative of some simple complex valued functions. In some cases, the derivative existed, and in some cases, we also saw that there are some functions where the derivative does not exist. We also discussed the relation between the continuity and differentiability of a function. Now, in this part, we are going to study some formulas which are going to help us in calculating the derivatives of functions. Now, as we know that we defined the derivative of a complex valued function in exactly the same way as we defined it for real valued functions. So, the proofs of these formulas are very similar to the ones that we did for real valued functions. Now, recall how did we define the derivative of a complex valued function. So, we defined it in this way, or equivalently, the derivative is given in the following way. So, the proofs once again are very similar to the differentiation formulas for real valued functions. Now, let's begin with our first property. So, the first property is basically very simple observation that the derivative of a constant is 0. Okay, so there is no change in the function. So, of course, the derivative is going to be 0. So, for example, if I want to calculate the derivative of, let's say, complex number 10, then the result says that since 10 is a constant, so the derivative is going to be 0. Now, let's consider another complex number, let's say iota. Now, iota is a constant, so that's why the derivative is going to be 0. The next formula is basically this power rule, where we have this power function z is to power n, and the formula says that if we want to calculate the derivative of this, then it is going to be equal to n z is to power n minus 1. And once again, let me remind you, it is exactly the same formula that we did for real valued functions. Now, let's see how this formula helps us in saving time when we are calculating the derivatives of different complex valued functions. Now, let's consider this derivative. I want to calculate the derivative of z is to power 15. Now, let me remark here, if I want to use the definition of derivative that I just recalled, then it is going to be a very tedious calculation. It is going to take us many pages if we want to use the same definition. Now, this power rule helps us in reducing the time. So, the power rule says that here n is equal to 15. So, that's why this is going to be equal to 15 multiplied by z is to power 15 minus 1. So, it becomes basically 15 z is to power 14. And in basically 3 lines, we are able to calculate the answer. And if we use the definition of derivative in this case, then once again, let me tell you that it's going to take us many pages. The next formula is basically the fact that if I multiply a constant with a complex valued function, then this constant can easily be taken outside this derivative, and it will not affect the derivative process. So, in other words, if I've given a constant, let's say 10, and if I want to calculate the derivative of 10 into some complex valued function f of z, then this is the same as calculating the derivative of f of z and then multiplying the result with 10. Okay. So, similarly, if I have a function, let's say 10 into z raised to power 3, then the derivative becomes 10 d by dz, z raised to power 3, and of course we can use the power rule to calculate this derivative, so it becomes 3 z square. So basically it becomes 30 z square. Now, the next formula, once again very similar to the real case. So it says that if I want to calculate the derivative of the sum of two functions, it is going to be equal to the sum of the derivative of the functions. So for example, if I'm given 2 plus z square, for example, then this result says that I can take the derivative separately and it will not change the derivative. And we know that what is the derivative of z square, and 2 is a constant, so the derivative is going to be 0. Okay, and we know the derivative of z square, so it becomes 2 and z. So at the end the answer is 2z. Similarly, we can calculate whenever there is a summation of functions. So of course, if there is a sum of, let's say, 10 functions, then this formula can also be applied. Okay, so for example, it will be applied iteratively. So for example, if I am given d by dz f1 up to so on fn, then this is equal to d by dz of f1 up to so on plus d by dz of fn, and up to so on. And of course, if there is a negative sign in place of positive sign here, then this formula also holds. The next formula is basically known as the product rule. So because there is a product of two complex valued functions here, f of z and g of z, and this formula provides a simple way of calculating the derivative of the product of these two functions. So the formula says that the derivative of this product is equal to f of z into the derivative of g of z plus g of z into the derivative of f of z. And if we use the prime notation, so in place of d by dz of g of z, if we use the prime notation, okay, so here the notation is d by dz of g of z is equal to g prime of z, and similarly d by dz of f of z is denoted as f prime of z. So using this notation, our formula becomes simple. So it becomes f of z into g prime of z plus g of z plus f prime of z. So it's very simple to remember this formula. If in some factor we are not taking the derivative of f of z, then in the next factor we will be calculating the derivative. And similarly, we can easily generalize this thing to functions where there is a product of, let's say, 3 functions or more functions. Now let's see how to prove this formula. So to prove this formula, we denote this function f of z into g of z by w, and by using the definition of the derivative, w prime of z is equal to limit delta z approaches to 0 w z plus delta z minus w z divided by delta z. So this is the definition of the derivative. And if I want to calculate this thing, then we need to calculate, for example, first this factor, and then we will take the limit. And to calculate this factor, let's first calculate what is w of z plus delta z. So w of z plus delta z is equal to, okay, so in place of z, now we have z plus delta z. So of course, if it is w is equal to f of z g of z, so we just replace z plus delta z here in this case and in this case. Okay, so it becomes f of z plus delta z g of z plus delta z. So this is w of z plus delta z. And of course, what is w of z? This is just f of z g of z. So we have the following equation: w of z plus delta z minus w of z is equal to this thing. Now to prove the result, we add and subtract this factor f of z into g of z plus delta z. So over here we have added this thing and subtracted this thing over here, and of course it will not affect the expression. And in the next case, we just simplify them in the following way. So over here in the first two terms, we can see that g of z plus delta z is common, so we can just write it down in the following way. So this is basically the first two terms. Over here g of z plus delta z is common, and in the next two terms we can see that this is f of z g of z plus delta z minus f of z g of z. Now over here f of z is common, so we can just write it down in the following way: f of z g of z plus delta z minus g of z. Now on the left side we can see that it is w of z plus delta z minus w of z. Now to calculate the derivative, then we divide both sides with delta z. Okay, so dividing by delta z, we get the following expression. There is no change on the right hand side except for the fact that we just divided with delta z. Okay, so the rest of the things are the same, and of course in the next step, if we want to calculate the derivative, we should take the limit on both sides. So taking the limit, we get the following expression. So the limit delta z approaches to 0, w of z plus delta z minus w of z divided by delta z is equal to, so we are just taking the limit. Okay, so limit delta z approaches to 0, the rest of the things are the same, and similarly taking the limit of the second term, limit delta z approaches to 0, f of z, and the rest of the terms are same. Now we are here. Now once again we can use different properties of limit. So for example, over here we have product of two functions. So this is the first function and this is the second function, and in the second case, once again we have product of two functions. So the limit of f of z multiplied with this function. So this is going to be equal to so limit delta z approaches to 0, g of z plus delta z multiplied with limit delta z approaches to 0, f of z plus delta z minus f of z divided by delta z, plus we have limit delta z approaches to 0, f of z, and limit delta z approaches to 0, g of z plus delta z minus g of z divided by delta z. Now let's observe. So this expression, when delta z approaches to 0, so this becomes g of z, and the second expression, so this is basically the definition of the derivative of f of z. So this is basically f prime of z, and in the second term we can see that this expression remains the same because there is no delta z involved in f of z, so it is just a constant for delta z. So that's why it is just going to be equal to f of z, and then this expression is basically the derivative of g of z. Okay, so this is basically g prime of z, and this factor is basically f prime of z. So hence we have the following expression. So g of z f prime of z, so the first term, plus f of z g prime of z. So this is the proof of this product formula. Now let's use all of these formulas that we have proved so far to find the derivative of this polynomial function. So the polynomial function, it's an degree n polynomial function, and all of these coefficients are complex numbers. So let's see how we can apply these formulas to calculate this derivative. Okay, of course it is z over here. Z is the complex variable. So d by dz a naught a1z up to so on an z raised to power n. Now the first property or first formula that we are going to use is, if we have derivative of the sum of functions, then it is going to be equal to the sum of the derivative of the functions. So it becomes d by dz of a naught plus d by dz of a1z up to so on plus d by dz of an z raised to power n. The next property that we are going to use is, so a naught is a constant, and we saw that the derivative of a constant is always 0. So that's why this becomes 0. Okay, and the next property that we are going to need it. So now it is the derivative. So the second term is derivative of product of a constant with this variable, or we can say it's a function. So when a constant is multiplied with a function and we are taking its derivative, then we can easily write down this constant outside this derivative notation. So, and if we apply the rule, this rule for all the terms, so it becomes a1 d by dz of z plus a2 d by dz of z square up to so on plus an d by dz of z raised to power n. Now the next formula that we are going to use is basically the derivative of the power function. So in this case, power is 1. In the first term, the power is 1, n is equal to 1, and in the next term, the power is 2, and up to so on, the power ends to n. So applying this power rule again and again, we get the following expression: a1 plus 2a2z plus 3a3z square up to so on plus n an z raised to power n minus 1. Now this n is basically coming from the application of this power rule. Okay, so this is the derivative of this polynomial function, where we have used some properties that we have proved so far, or we have seen so far. Now the next property is basically the chain rule. It is very useful and very powerful rule that helps us in calculating the derivatives of different complex valued functions. Now it helps us when we are given two functions and there is a composition of these two functions. Okay, so if functions f of z and g of z are given, then recall that their composition is defined in the following way: f composition g of z is equal to f of g of z. Okay, so that's how we can define the composition of these two functions. Now if we are given composition of two functions, then we can apply this chain rule in the following way. So this chain rule says that if we have this f composition g, so this is basically f circle g of z. So, and if we are calculating the derivative of this composition, then this is going to be equal to f prime of g of z into g prime of z. Okay, so over here we are considering this f as a function of g of z, and then we are calculating its derivative, and the second step we are multiplying this thing with the derivative of g prime of z. So sometimes we call it outside inside rule. So why we call it outside inside rule? Because we have over here we are taking the derivative of the outside function, because f is basically the outside function and g is inside function. In the first step we take the derivative of outside function, which is f prime of g of z. Okay, so we just consider f as a function of g of z. We will see in few moments some example where it will be more clear. And in the next step we are calculating the derivative of the inside function. So that's why sometimes it is also known as outside inside rule. Now let's apply this rule to this derivative. Okay, so over here the variable is z, because we are taking derivative with respect to the variable z. So the function is given and we want to calculate the derivative of the cube of this function. Now remember, in this case, if we don't have a chain rule, then once again it will be very complicated to calculate the derivative using the formulas other than the chain rule. Okay, so how chain rule helps us? Now over here, what is the outside function and what is the inside function? To figure out what is outside function, now observe this thing. It is basically cube of some function. So basically whatever is inside of this cube, outside we are taking the cube. So basically cube is basically the outside function, and then inside function is f of z. Okay, so in other words, if we define h of z to be z cube, and then this function, okay, so this function which is f of z whole cube is basically h composition f of z. So which is of course equal to h of f of z, and since h of z is z cube, and so when we replace this z with f of z, so it becomes f of z cube. So the definition of h of z says that it is equal to z cube. So whenever we replace z with something else, so in this case with f of z, so it becomes f of z cube. So that's why it is composition of two functions. So what is outside function? So outside function is z cube, and what is the derivative of z cube? We know by power rule it is 3z square. So by chain rule, first we take the derivative of outside function. Okay, so let me write down here what is h prime of z. It is basically 3z square. Now according to chain rule, we consider this outside function as a function h of f of z and not h of z. Okay, So that's why we have the following derivative. So the outside function has the following derivative 3. So instead of z, we have f of z and then square. So this is the derivative of the outside function, which is this z cube. And what is the inside function? This is f of z. So then we multiply it with the derivative of f of z. So that's how we take the derivative of this f of z cube. Now we can easily calculate the derivative of this f of z. So 3 f of z square. So once again it is sum of 3 terms, so we can distribute, or we can take the derivative of the separate terms and then add them, and the first term is z cube, and z cube has the derivative 3z square. The second term, 2 iota, are constant, so we can just write down constants over here without any change, and z square has the derivative 2z, so it becomes 2z, plus 4 is a constant, so its derivative is 0. So this is the derivative of this cube of f of z, where f of z is z cube plus iota 2z square plus 4. So we use chain rule to calculate this derivative, and once again, if we don't use chain rule in this case, then it becomes a relatively complicated calculation. So in this discussion we studied some differentiation formulas, the sum rule, the product rule, and the chain rule. These formulas are useful when we are calculating the derivatives of complex valued functions.